Welcome to this video on predicting material failure. We will explore the mechanics of stress, strain, and material survival in various applications. Let's explore the hidden world of internal forces. An external force applied to an object creates internal resistance, which we measure as stress. Stress is force per unit area. For example, failing a 20 millimeters mild steel bar requires over 79 kilonewtons of force. Deformation is the visible consequence of these internal forces. Strain describes this physical deformation in response to stress. It is a non-dimensional quantity, expressed as the change in length divided by the original length. Stress and strain represent a fundamental duality. Stress is the internal cause or resistance, measured in pascals. Strain is the external effect or deformation, which is unitless. Hooke's law acts as the material translator, linking stress and strain through the elastic modulus, E. In the linear limit, deformation is directly proportional to stress. This modulus varies significantly, with rubber having a low modulus and steel a high one. Stress comes in different forms. Normal or axial stress acts perpendicular to the cross-section. Shear stress acts tangential or parallel to the surface. Bearing stress is the compressive force transferred perpendicularly between two interacting surfaces. When a longitudinal load is applied, materials deform laterally. Poisson's ratio defines this lateral contraction. A cork has a ratio near zero, showing no lateral expansion, while rubber's ratio of 0.5 indicates constant volume under compression. The stress-strain curve defines a material's identity. The initial elastic region is reversible. Beyond the yield point, permanent plastic deformation begins, leading through strain hardening to the ultimate tensile strength, and eventually to necking and catastrophic fracture. Elastic deformation is fully reversible, as atomic bonds temporarily stretch. Plastic deformation is permanent, occurring beyond the yield point, where atomic bonds physically break and shift. Plastic deformation is crucial for manufacturing processes like bending and forming. The failure spectrum separates ductile and brittle materials. Ductile materials, like steel, show significant warning signs, such as yielding and necking, and absorb a lot of energy. Brittle materials, like concrete, fail suddenly, with no visible necking and low energy absorption. Engineers must consider the difference between the engineering model and true stress. The engineering model assumes a constant original area. The true reality calculates dynamically based on the shrinking neck area, revealing that work hardening continues up to the moment of rupture. The factor of safety is the engineer's net for survival. It is the material strength divided by the maximum allowable stress. This analysis guarantees that structures remain safely away from failure thresholds, preventing catastrophic failures, for example, in aviation. This video has explored the core concepts of predicting material failure. Thank you for watching.